Welcome back, everybody, to my video series on special relativity. So in the last video, we derived this expression for t, t primed. Basically, it gives the time of the person inside the container, this person here, as a function of t, which is the person outside the containers, their time, and L. And L is this sort of mysterious quantity that we want to talk about and dive into a little more. I said L is a parameter, and we really need to think of it as a parameter, something we can adjust. So to take this picture a little further and to move on from here, we're going to sort of redraw it. And we're going to redraw it like this. So we have X, Y, we have our box, okay, that's sitting on the X-axis. And what we want to do is we want to say the photon is here. The photon is sitting at L, and remember we can adjust this L, stretch it or collapse it. And we'll say that x, little x, all the way to the photon is that dimension. We'll call this, assuming it started at the origin, we'll call this Vt, and we will call this L. So what we obtain is an expression that x equals L plus Vt, and that L equals x minus Vt. Okay, so we're going to sort of tuck that away for now, and we're going to start to ask how can we figure out what beta is in our equation up here, and how to get this in the form t is a function of, t prime is a function of x and t. So now that we know what x is, we just talked about x, we kind of need to figure out what beta is. So this photon, there's a couple thought experiments that we can do to answer this question. First of all, we can stick it, rather than in the middle, we can actually stick it in the corner. The thing we need to know about light is that light radiates in all directions, right? It radiates in all directions. So the question is, what happens when you move this container? Okay, so let's bring it to a moved point, some later point, which we'll refer to using sort of the same ideas as before. So now we've traveled some distance. What happens to this photon if it shoots straight up? Okay, so now the photon is here. So let's say it shoots straight up in the container. Well, it was here, and we have some distances. We have this distance and this distance. Well, this is going to be Ct, or C delta T, and we'll call it delta TA, because this is still our delta TA jump, sort of, where this is V and this is V. This distance is V delta TA. And then this height we're going to call y equals y prime. Basically, y in the unprimed and primed reference frames are the same, because the motion of this thing, is in the x-axis. It has nothing to do with the y-axis, so there's no contraction there. Okay, so basically we have a Pythagorean right triangle here, so we can do a little bit of algebra. So we get v squared delta ta squared plus y squared equals c squared delta ta squared. Okay, so we have this delta ta, but more importantly, we want to ask, well, what about in our primed reference frame? Well, we know that y equals c delta ta, okay? And delta ta, if you recall, a t prime, sorry, this is primed. This is primed. In our primed reference frame, it's obviously just straight up. It's just a straight up path from here to here for the primed reference frame. So it's C delta TA. And delta T is beta times T, make sure I get this right, V over C squared minus V squared times L. Now, but in this case, in this specific case, L equals 0. Remember, L is a parameter. L is this parameter that we're talking about. And for this case where the photon goes straight up, there is no L. L is 0. You can do this with a straight vertical line. So what you get is y equals C beta T. Cool. So we have this closed form. Well, it's not T. It'll be delta TA. okay, because L is 0, and this term drops out. Okay, so going back to our Pythagoras sort of relation, we want to get an expression for y. So we get y squared equals, let's take the delta TA square out. So we get c squared minus v squared. Okay, and now I want to just basically equate these two things. So y is going to be square root. I'm not going to get pedantic here and do plus or minuses. We'll assume we're talking about real numbers, not imaginary numbers. Okay, so y is equal to delta TA times the square root c squared minus v squared. Make these two things equal, we get, and let's just bring it up here, you get delta TA is equal to square root c squared minus v squared equals c beta delta TA. Okay, well our delta TA's cancel, and then we get an expression for beta. We get this over c. Okay, cool. So now we have sort of a closed form expression for beta that's in terms of other variables of c and v. C and v, which we are assuming constants. Okay, so that answers the question, what is beta? How about answering the question about this function? How can we get L in terms of something else? So we want to get L in terms, or T in terms of x and t. So what we need to do is we need to get an expression that relates, well, how does x prime relate to our length L? So this is what we want to show next. So we're going to do the exact same experiment, except we're going to have the photon starting out on the bottom, and then it starts out like this, and then in the next frame, the photon is going to be over here. Now this is actually a case that we've already covered in our initial thought experiment that we did. So it's not too hard to see what's going on here. Okay, so we want to ask, what is x prime? Well, x prime is obviously just c delta TA prime. And delta TA prime is going to be beta times delta TA, okay? Scrolling up a little bit, minus v over c squared minus v squared times L. Okay, now delta TA in this little experiment, where we do this jump, okay, it's delta TA. Remember, this is T0, T1. We talked about all this. We showed that delta TA for the absolute reference frame, or I shouldn't say absolute, but the stationary reference frame, this person over here, is going to be equal to L over C minus V. So we know that we can substitute this in. So you get C beta L over C minus V. I'm going to leave a little bit of room. You'll see in a second. And then we get minus V over C squared minus V squared L. Okay, so I want to normalize this. We'll do C plus V. There's a lot of this that goes on in this derivation. I want to get that denominator the same, right? So we get C beta equals, we get LC plus LV minus LV, all over C squared minus V squared. So this is looking to be something really nice. Remember what we're doing here. We're showing x prime. These cancel, obviously. So these guys, LC, LV, and LV, go away. And then we are left with, let's write it like this. We're going to write c squared over c squared minus v squared times beta times L. Okay, so what's beta? Beta is, we've already defined beta. Let's copy it. We figured it out earlier in this video. Let's copy that definition. Oops, let's copy it down here. This is what beta is. Let's get rid of some of this other junk. So beta is square root c squared minus v squared over c times L. And then we get, well, this is going to cancel, so we get 1c left on top. And then we have half minus 1 which is negative half on the square root sign. So we get c over square root c squared minus v squared times L. And you will notice that this is simply equal to 1 over beta times L. Okay, so this is actually our contraction relationship that we had talked about. We rationalized that there must be some contraction, and now we're showing that it's true. All right, so one further thing we're going to do here to get this in the standard Lorentz notation is we're going to define gamma to equal 1 over beta. And this is the gamma that you will see in the standard derivations. So what does this mean? Well, if gamma is 1 over beta, first of all, gamma is equal to c over square root c squared minus v squared. And then, of course, this guy down here is just equal to gamma L. Now, what's L? We also gave a definition for L earlier that I'm going to grab quickly. We gave that right here. L equals x minus vt. So we're getting very close to sort of the standard result that we're used to seeing. L is x minus vt. So then we get gamma times x minus vt. Okay, I'm going to stop this video here, but I think we've shown another step in the chain here, how you get x prime. Remember what x prime is. It's the position of that photon inside the box, to the person inside the box, what they see. And we're saying that it's this function of x, and t. So we're getting really close. Okay, so please like and comment and subscribe and just tell me what you think.